In early 1945, near the shores of Japan, an American F4U Corsair fighter went down after its engine failed during a mission. The pilot bailed out just before the plane hit the freezing Pacific waters. Within hours, Japanese patrol boats arrived at the crash site. What they found would become one of the most valuable intelligence discoveries of the war's last months. For nearly 3 years, Japanese pilots had fought against this powerful American fighter in places like the Solomon Islands, Rabaul, the Philippines, and now above their own homeland. They had come to respect its incredible speed, heavy firepower, and strong design. But never before had they managed to capture one in perfect condition. Now they had a chance to study it closely, its design, its engineering, and what made it so advanced. This wasn't just about a captured plane. It was about Japan realizing how far American technology and industry had advanced. When Japanese engineers studied the Corsair, they discovered the precision, materials, and design ideas that made it superior. These findings changed the way they thought about their own aircraft design and production capabilities. The Corsair the Japanese recovered was the result of years of American innovation. Designed back in 1938 to meet strict Navy requirements, the F4U Corsair evolved into one of the most feared aircraft of World War II. Its unique gull-shaped wings, massive Pratt & Whitney R2800 double wasp engine, and impressive performance made it instantly recognizable. More importantly, it achieved something Japanese aircraft had long struggled with: a perfect balance of speed, power, endurance, and toughness. The idea for the Corsair began in 1938 when the U.S. Navy asked for a fighter that could fly faster than 400 miles per hour in level flight. At that time, most fighters couldn't even reach 350 mph. The Navy also wanted it to take off and land on aircraft carriers, have long range, carry heavy weapons, and even drop bombs. The company Chance Vought accepted the challenge. Led by chief designer Rex Beisel, the team decided to build the fighter around the most powerful engine available, the Pratt & Whitney R2800 double wasp. This 18-cylinder, 2-row radial engine produced 2,000 horsepower, nearly twice that of most fighters of its day. To use this power effectively, they built a huge 13-foot propeller, the largest ever put on a fighter. The challenge was how to keep the propeller from hitting the ground while keeping the plane strong enough for carrier landings. Their solution gave the Corsair its signature look, the inverted gull wing. Instead of straight wings, they angled downward from the fuselage and then leveled out, forming an M shape when viewed from the front. This design allowed shorter landing gear and better clearance for the large propeller, while also improving aerodynamics. The first prototype, called XF4U-1, took flight on May 29, 1940, with test pilot Lyman Bullard Jr. at the controls in Stratford, Connecticut. On October 1st of that same year, the Corsair became the first single-engine American fighter to exceed 400 mph, hitting that mark with tailwind assistance during a test flight. Its top speed in level flight was 378 mph at 23,500 feet, an amazing achievement for that era. By late 1942, the F4U-1 Corsair began reaching operational squadrons. The first Marine unit to receive it, VMF-124, deployed to Guadalcanal in February 1943. But the Corsair's first battle didn't go well. On February 14, 1943, in what became known as the St. Valentine's Day Massacre, American forces lost 9 aircraft, including 2 Corsairs, while Japanese pilots lost only 1 Zero fighter. This heavy loss forced U.S. commanders to rethink their tactics. It was a harsh lesson. Technology alone couldn't win battles. Strategy and experience mattered too. American pilots soon adapted and discovered the Corsair's true strengths, speed, and power. Instead of turning tightly like Japanese planes, they used boom and zoom tactics, diving at high speed to attack, firing, then climbing away before the enemy could respond. Lieutenant Kenneth A. Walsh mastered these tactics and became the first Corsair ace on May 13, 1943, eventually downing 21 enemy aircraft. As the war continued, the Corsair earned a fearsome reputation. Marine pilots flying from rough island airstrips used the plane's toughness to their advantage. It could take heavy damage and keep flying. Armed with 650 caliber Browning machine guns, it had devastating firepower. Later versions swapped these for 20mm cannons, though many pilots preferred the reliability of the machine guns. The Corsair was also adapted to carry bombs, rockets, and napalm, making it effective for ground attacks. During the Battle of Okinawa in 1945, Corsairs flew countless missions in support of ground troops, earning the nickname Angels of Okinawa. To Japanese pilots, the Corsair was a nightmare in the sky, fast, durable, and deadly. But the real shock came when engineers got to study the captured one up close. Japan's top research centers, the Yokosuka Naval Air Technical Arsenal near Tokyo and the Army Aviation Technical Research Institute at Tachikawa, took charge of the investigation. These centers had been studying wrecked Allied planes for years, but most were damaged or incomplete. This time, they had a nearly intact operational American fighter, an invaluable opportunity. The Yokosuka facility had been Japan's main naval aviation research center since 1932. By World War II, it was staffed by thousands of engineers and designers who developed advanced aircraft for the Japanese Navy, although the actual manufacturing was done by major companies like Aichi, Nakajima, and Mitsubishi. These engineers were highly skilled, but even they were amazed by what they discovered inside the Corsair. When the salvaged Corsair reached Yokosuka in early 1945, it was one of the most modern American fighters recovered in mostly intact condition. The plane had taken on salt water during its forced landing, but its basic structure was sound. Recovery teams had kept it from sinking and moved it to Yokosuka's secure technical area for study. The first checks looked at overall condition. Despite immersion in seawater, much of the Corsair stayed whole. The huge Pratt & Whitney R2800 double WASP engine would need to be completely taken apart and cleaned, but the airframe showed no combat damage. That mattered a great deal. Earlier Allied captures were usually badly wrecked, making it hard to tell what was original design and what was battle damage. Japanese experts began by photographing and measuring everything. They recorded every dimension. Wingspan 40, FT 11.7 in, length 33 FT 4 in, and height 15 FT with wings down or 16 F 2.3 in when the wings were folded for carrier stowage. The inverted gull wing immediately drew attention. Japanese designers knew the shape had aerodynamic and structural benefits, but they also saw how hard it was to make. Getting the compound curves and exact angles required advanced tooling and strict quality control that most Japanese factories were struggling to maintain late in the war. Inspectors were surprised to find that parts of the outer wing were covered with fabric instead of metal. The main wing spar area, armament bays, and the control surfaces, ailerons, elevators, and rudder all used fabric skin in places. Since by 1944-45 most modern fighters used all metal skins, this seemed odd at first. Further study showed the choice was intentional. During the Corsair's 1938-1940 design period, fabric was used where loads were small to save weight and conserve aluminum for critical parts. The fabric was a specially treated material that, when applied correctly, provided enough strength and weather protection while weighing much less than metal. This showed a mature understanding of where to use limited materials for the best performance. Taking the wings apart revealed construction techniques that impressed and concerned the Japanese engineers. The main wing spar, the key structural member that takes flight loads, was a huge, high-quality forging. American metallurgy produced aluminum alloy forgings with strength and uniformity that Japanese facilities found hard to match. The spar's size and load capacity were greater than anything in comparable Japanese fighters and highlighted a major industrial difference. American plants could make large, complex forgings with consistent quality, while Japanese builders often used built-up structures from many smaller parts. Inside the wing, stamped aluminum ribs showed remarkable precision and uniformity. Each rib matched the next almost exactly, which meant manufacturing processes had very tight quality control. By contrast, Japanese aircraft production was seeing growing inconsistencies as the war went on, with parts sometimes varying from plane to plane. Attention shifted to the weapons fit. 6 Browning 50 caliber machine guns mounted in the wings gave the Corsair heavy firepower. The gun installation was compact, reliable, and built for easy maintenance. What stood out to Japanese examiners was the completeness of the systems. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms all worked together smoothly. The guns themselves were examples of precision manufacturing. American ordnance production had reached reliability levels Japanese industry admired. The Browning M2 design had been refined over decades and was produced in huge numbers with consistent quality. Japanese technicians recognized manufacturing methods and standards they could not reliably reproduce. They also found 150 pounds of armor plate protecting the cockpit and a 1.5-inch thick bullet-resistant glass panel behind the windscreen. Japanese fighters had mostly given up heavy armor to stay light and maneuverable, and early successes by the Zero seemed to support that approach. But as American fighters became more powerful and heavily armed, lack of protection often proved deadly. The Corsair showed that substantial armor could be added without ruining performance, thanks to the huge power of the R2800 engine. The engine dominated the technical study. The Pratt & Whitney R2800 Double Wasp was a peak example of American aero engine development. 18 cylinders in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower. Japanese engineers had seen this engine in captured planes before, but never in such good condition for detailed analysis. The engine's construction revealed manufacturing capabilities that seemed almost unbelievable. Cylinders were machined to tolerances of thousandths of an inch. Pistons, connecting rods, and crankshaft parts had surface finishes and dimensional accuracy that Japanese engine makers struggled to reach. The 2-stage supercharger designed to keep power at high altitude used complex internal passages and precisely fitted rotating parts. Japanese attempts to build similar superchargers had largely failed because of manufacturing limits. Perhaps most impressive was how reliable the engine was while delivering rated power for hundreds of hours between overhauls. Japanese engines, even new ones, often could not hit theoretical power numbers and needed frequent maintenance. The R2800's consistent performance came from better metallurgy, superior lubricants, more precise machining, and stricter quality control. The propeller system was revealing, too. The Hamilton Standard hydraulic propeller, 13 ft4 in diameter with variable pitch, showed advanced aerodynamic design and hydraulic control engineering. Japanese engineers understood propeller theory but did not have factories capable of making such large propellers with the needed precision. Looking through the whole airplane, they saw repeated patterns of high-quality work. The landing gear was complicated but made with exacting standards. The cockpit had a fuller set of gauges and controls than any Japanese fighter. The fuel system used self-sealing tanks with several layers of rubber compounds that swelled when pierced, stopping fuel loss, a feature most Japanese aircraft did not have. The electrical wiring was neat and robust, powering many systems with proper insulation and tidy routing. Most striking was the uniform quality of materials and workmanship. Big structural parts and tiny fasteners alike showed consistent standards. Aluminum alloys had even properties, steels were heat-treated correctly, and finishes were smooth and professional. The whole plane felt solid and built to last. That contrasted sharply with Japanese aircraft production in 1945. Wartime shortages forced use of substitute materials. Aluminum quality declined. Skilled workers were drafted into the military, and factories ran under the constant threat of American air raids. Quality control slipped as speed and output were prioritized over consistency. The Corsair examination happened while Japan faced probable defeat. American B-29s were systematically destroying Japanese cities. The Navy had been shattered at Leyte Gulf. The Philippines had been liberated. Iwo Jima had fallen and Okinawa was under assault. In this grim context, studying the Corsair carried heavy meaning. It was not research for future triumphs, but a stark confrontation with technological reality. Engineers at Yokosuka and Tachikawa wrote technical reports recording measurements, manufacturing observations, and assessments of American capabilities. Their tone was professional, but the implications were clear. In almost every area they inspected, American technology outmatched Japanese abilities. The gap was not minor or easily fixed. It reflected decades of industrial growth, huge investments in tooling and research, complex supply chains, and resources Japan lacked. By the end of the war in August 1945, at least 2 Corsairs had been captured. Photographs show some captured Corsairs with patched wings and repaired fuselages, and evidence suggests technicians restored at least one toward flying condition. Whether it actually flew again is unclear, but repair attempts show serious efforts to make captured examples operational for testing. When American occupation forces reached the Yokosuka Naval Air Technical Arsenal in September 1945, they found clear evidence of Japan's technical intelligence work, captured Allied planes strewn about the facility. Reports, drawings, and photos documenting efforts to understand enemy technology. American intelligence officers collected these materials because they revealed what Japanese engineers had learned. The story of Japan's study of the F-4U Corsair is more than a technical case study. It symbolizes the wide gap between American and Japanese aviation by the war's end. When the Corsair first saw combat in early 1943, Zero pilots could still compete through better tactics and pilot skill. By 1945, though, even skilled Japanese pilots in newer planes had little chance against well-handled Corsairs. The aircraft's technical edge, combined with massive American numbers and superior pilot training, created hopeless odds. Officially, the Corsair achieved an 11.1 kill ratio against Japanese aircraft. American Corsair pilots shot down 2,140 Japanese planes while losing only 189 Corsairs to enemy action in World War II. Those figures reflect not only the Corsair's superiority, but the broader strengths of the American war effort. Better training, stronger logistics, immense production capacity, and advanced technology at every level. Japanese engineers studying the captured Corsair could measure the performance gap, analyze manufacturing differences, and calculate resource shortfalls. Their reports stand as frank acknowledgments that Japan could not match American industrial power. The Corsair continued serving long after World War II. It fought in the Korean War, 1950-1953, proving valuable in ground attack and close support roles even as jets took air superiority tasks. Several foreign air forces, including France, used Corsairs in colonial conflicts into the 1960s. The type's final combat actions came in July 1969 during the so-called Soccer War between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, flying an F-4U-5, shot down 3 Salvadoran planes, including 2 FG-1D Corsairs, the last recorded combat victories by the type, ironically against other Corsairs. From its first flight in 1940 to its last combat sorties nearly 30 years later, the Corsair proved one of aviation's most successful and long-lived fighter designs. For Japan, the Corsair encounter was part of a broader reckoning during the American occupation. Engineers and scientists who had struggled with shortages and production limits during the war now worked with occupation authorities to rebuild industry. Lessons from studying American technology, including the Corsair, influenced post-war Japanese manufacturing, an emphasis on quality, precision, and continuous improvement that helped shape modern Japanese industry. The Corsair, recovered in early 1945, was more than a downed fighter. It was proof of engineering excellence and advanced manufacturing that Japanese aviation had sought for years. The lessons arrived too late to change the war's outcome, but they helped shape the peace. By examining this American fighter, Japanese engineers faced the full scale of the challenge their country had confronted. They had fought with courage and skill, but those qualities could not overcome the vast technological and industrial advantages of their opponent. The reports on the Corsair, later found by American occupation forces and preserved in archives, remain silent witnesses to the moment when one nation's engineers confronted another's capabilities. The examined Corsair likely disappeared during the chaotic post-war period, probably scrapped, but its legacy lives on in the lessons it taught about what careful design, adequate resources, and precise manufacturing can achieve. Japanese aviation rose again after the war, but never again did its engineers underestimate what American industry could produce when given the capacity, science, and resources to realize ambitious designs. The 1945 study of the F-4U Corsair stands as a watershed moment when Japan's aviation community fully grasped the technological chasm opened by the war, a lesson written in aluminum alloys, precision forgings, and manufacturing tolerances that spoke louder than words.